in a rigid rotor problem, you have two particles. Particle 1, particle 2. The distance between them is fixed. So it's like a dumbbell, basically. So the distance between them is fixed. Of course, there isn't anything between them, right? It's just that the distance is fixed. So this distance r is constant. Okay. So in the case of a rigid rotor problem, you're going to find that the internal motion, okay, since they have to keep the same distance no matter where they are, all right? So the total kinetic energy would just be the translational motion, right? Your center of mass would be right here, right? Somewhere here. You'll be tracking the center of mass. The motion of this dot right here, okay, would be the motion of the center of mass. So the energy associated with that we call the translational energy of the pair, right? Now, the relative motion of the two, okay, since they can't change the distance between them, is essentially what we would call a rotational energy. Okay? So in a classical description of this, the total energy will just be the translational energy plus the rotational energy. And classically, that rotational energy is just L squared over 2I. Okay, what's L squared? You can think of this thing as rotating, right? So L squared is your angular momentum. So L squared is the square of the angular momentum vector. And I is the moment of inertia. But instead of mr squared, remember when we did the particle and a sphere? Think of a particle and a sphere as having a fixed distance from the origin, right? Well, this is essentially a particle and a sphere, except there's the mass. Instead of using the mass, we use the reduced mass. So this problem effectively is a particle in a sphere problem, except that instead of mass here, since we're dealing with two particles, the particle in a sphere in this case is a fictitious particle that has a mass equal to whatever the reduced mass is of those two particles. Okay, so the quantum mechanical solution to this problem, quantum mechanical treatment to this problem will give you pretty much the same solution as a particle in a sphere. So your energies, if you remember, for a particle in a sphere is, what were the energies for a particle in a sphere? L times L plus 1 h bar squared over 2I, right? And this one, what did you call that? That's your B, right? Rotational constant. So same thing here, except that we're going to use a more generic letter for rotational quantum number. We're going to use J instead of L. So it's J times J plus 1 times B. Same thing. B, rotational constant, is h bar squared divided by 2I. But like I said, your I, your moment of inertia, is mu r squared instead of mr squared. What's our wave function? So in this particular case, all right, for your internal coordinates, instead of having x, y, and z, okay, it's convenient to use spherical polar coordinates, r, theta, and phi. Why? Because that simplifies your problem. R is a constant, right? So you don't need r anymore in your function. So your function will just depend on theta and phi. In fact, this is basically a particle on a sphere problem. So you just need two angles to define the relative coordinates of the two particles. So you can just define your theta and phi as the angle with respect to the z-axis and the angle with respect to the x-axis of your projection. Okay? So your psi is spherical harmonic, same psi as for your particle on a sphere. Okay? Except that your L, instead of L, we're going to use J. Okay, so in lieu of L, we're going to use the quantum number J. Instead of M or M sub L, we're going to use M sub J. Same thing. Same restrictions. J equals 0, 1, 2, 3, 4, and so on. M sub J would go from negative J to positive J. Negative J plus 1, all the way to positive J. Okay, so what would be the allowed energies for our particle on a sphere? The allowed rotational energies. What's the lowest allowed rotational energy? J equals 0, right? That's going to be 0B, right? What's the next allowed rotational energy level? J equals 1, right? 1 times 1 plus 1 times B, that's 2B. So J equals 1 would be 2B. How many ways can it have an energy equal to 2B? What's the degeneracy of this level? 3 ways, right? M sub j equals -1, 0, and +1. What's the next allowed energy level? J equals 2. Okay, so J equals 2. What's the energy for J equals 2? It's gonna be 2 times 2 plus 1B, so that's gonna be 6B. So 0, 2, 4, 6. So 6B is right here. How many ways can you have J equals 2? 2J plus 1. 2 times 2 plus 1. 5 ways. What are those 5 ways? 1, 2, 3, 4, 5. They correspond to M sub J equals -2, -1, 0, +1, +2. Okay? So those are the allowed energy levels, allowed rotational energy levels for a rigid rotor. Now, why is it called a rigid rotor? Rigid means fixed, right? Distance between the two particles is fixed. Rotor means the energy is due to rotation in addition to translation. What's L squared psi? What's the square of the angular momentum of your rigid rotor? Same as before. So it's going to be J times J plus 1 times H bar squared, and it gives you back psi, right? So the allowed values for your L squared is J times J plus 1 H bar squared. What are the allowed values for LZ? LZ hat psi would give you back what? Just like before. M sub J in this case. Instead of little m, we use M sub J H bar. Okay? And if I were to ask you to sketch the vector diagram, the vector for, let's say, J equals 2, M sub J equals -1, what would that vector look like? So if this was your z-axis, and this is your xy plane, what would that vector look like? The L vector. It's going to be pointing down or up? Pointing down. The z component of the vector is going to be -1 h bar. So this is your angular momentum vector L, right? The magnitude of this angular momentum vector is how much? Square root of 6 h bar, right? Square root of 2 times 2 plus 1 h bar squared. So square root of 6 h bar. So we say that this vector is going to be precessing about a cone of uncertainty around the z-axis, right? So if the vector is here, how would you classically describe the motion of your molecule? You can imagine you have this dumbbell right here. It's going to be rotating that way, right? To have an angular momentum pointing that way. Remember your right hand rule, curl your fingers, your 4 fingers in the direction of motion, of the circular type motion, and then your thumb will be pointing in the direction of the angular momentum vector.